Hello all. Welcome to Module 2 of MAT201, Partial Differential Equations and Complex Analysis. In this lecture, we will look at the one-dimensional wave equation and derive it by considering the vibrations of a stretched string. So the wave equation is a second-order partial differential equation which is used to describe the small oscillations at fixed speed of some quantity y. The equation is dou square y by dou t square equal to c square times dou square y by dou x square, where c is the speed of the wave, t denotes the time variable, and x denotes position. For example, if a stretched string, as in a guitar or a violin, is plucked, the string will oscillate about equilibrium, and the vertical displacement of the string, y, would follow the wave equation. The wave equation describes many physical situations like gravitational waves, light waves, sound waves, and oscillations of strings. Let's derive the wave equation. We will derive the wave equation for the simplest case where it is applicable, a vibrating string. Start with an elastic string of length L, which is tightly stretched between two pegs. We want to know how the string moves if we give it a small displacement at time t equal to 0 and then leave it to vibrate. Place the string on the x-axis from 0 to L with the ends fixed at x equal to 0 and x equal to L. We want to find a function y of xt such that at any fixed time t0, the graph of y of x t0 gives the shape of the string at time t0. This two-variable function y of xt is called the position function for the string, and we want to derive the PDE satisfied by it. To simplify calculations, we make some assumptions. The mass of the string per unit length, which we call rho, is a constant. The string is perfectly elastic and does not offer any resistance to bending. Second, the tension in the string caused by stretching is so large that the effects of gravitational force can be neglected. Finally, every particle of the string moves only vertically, so that the deflection and the slope at every point of the string always remain small in absolute value. Consider the following figure. Line segment AB, where A is the origin 0, 0 and B is the point L0, is the equilibrium position of the string once we place it along the x-axis. The string is of length L and fixed at the end points, so the string is fixed at points A and B. These points do not move at any point of time. This string is now set vibrating. At time t, let the string be in the position shown in the figure. Take a small element pq of the string between the points p with coordinates x, y and q with coordinates x plus delta x, y plus delta y on the string. The tension T acts tangentially, and the tangents at p and q make angles psi and psi plus delta psi respectively with respect to the x-axis. Apply Newton's second law. Net force on the element PQ due to tension is the mass of PQ times acceleration of PQ. We'll evaluate the right side of this equation first. On the right hand side, mass of PQ is just mass per unit length times the length of PQ. Since PQ is a small element, we can consider the length of PQ to be delta X. So mass M is rho times delta X. As the string moves only vertically, its horizontal acceleration dou square x by dou t square is equal to 0. So the string moves with just the vertical acceleration dou square y by dou t square. So substituting for the acceleration, we find net force on PQ due to tension is rho delta x times dou square y by dou t square. Now evaluate the force due to tension called F. Again, we are looking at just the vertical component of the force. So the vertical component F is T times sine of psi plus delta psi minus sine psi. Since the angles are small, sine of psi is approximately equal to tan psi. So the force is T times tan of psi plus delta psi minus tan psi. Tan psi is just the slope of the tangent at the point P. But remember that the slope of the tangent is also given by the derivative dou y by dou x at that point. So tan psi is dou y by dou x evaluated at xt. Tan of psi plus delta psi is dou y by dou x evaluated at x plus delta x t. Substitute those, then the force is T times dou y by dou x at x plus delta xt minus dou y by dou x evaluated at xt. This force is equal to rho delta x times dou square y by dou t square. Rearrange the equation a little bit so that dou square y by dou t square equals t by rho times dou y by dou x at x plus delta xt minus dou y by dou x evaluated at xt divided by delta x. Take the limit q tends to p. Then delta x will go to 0. Then in the right hand side of our equation, dou y by dou x at x plus delta xt minus dou y by dou x at xt divided by delta x, as delta x tends to 0, becomes just the rate of change of dou y by dou x with respect to x, which is just the second order derivative dou square y by dou x square. So the equation becomes dou square y by dou t square equal to t by rho times dou square y by dou x square. Finally, let t by rho equal to c square, so that the equation is dou square y by dou t square equal to c square times dou square y by dou x square. This is the partial differential equation describing the transverse vibrations of a string, and it is called the one-dimensional wave equation.